Okay, we have learned how to slice the evolution in the time direction. We have learned how to slice, I'm sorry, the first thing was section, how to slice all possible symmetry transformations. But we are not done yet. Next thing we need to learn is how to dice. And dicing I'll try to illustrate by a very simple example from cardiac dynamics. So a typical problem in cardiac dynamics is that due to Euclidean symmetry of the equations of motion, localized solutions believe they have Euclidean symmetry, and the combination of translation and rotation leads to the behavior that one sees called spiral or spiral chaos if there is some number of such unstable solutions coexisting. So let's just consider a case of two unstable solutions coexisting, but on a domain which is significantly larger than their core sizes, so sizes on which the amplitude of the solution is considerable. So typical localized solution is maybe something that looks like Gaussian and falls apart very fast. So while in principle, once we have sliced the state space and gone to slice to reduce state space or the base space, dynamics there has no more Euclidean symmetry. It's been taken care of by, it's been reduced quotiented. The little coherent solutions, little localized solutions don't know that. They didn't get a memo. And they can actually move with respect to each other with very little cost. In principle, they can't because there is only one global solution. Solutions are not additive, these are nonlinear equations of motion. But if they're localized, the overlap of assuming individual and added solutions that can be added, the overlap between them is so small that the violation of assumption that they're independent is very small, and that shows up itself in the eigenfunctions of the system. And when you look carefully at the eigenfunctions, you realize that some of the eigenfunctions, especially, let's consider only the things that are almost marginal, they're localized either on one or the other one of these guys. And what they mean is then one can move them a little bit. Now, when you look carefully at the eigen vectors and eigenfunctions, you realize they're not marginal. You know, they're either weakly unstable, meaning that solution is trying to fall apart, or they're weakly stable, meaning that, you know, your guess of additivity is not quite right, and they are trying to, you know, lock themselves in some relationship. But these are very small effects. Now, these marginal eigenvalues that describe relative motions of the two cores are a big problem when you try to find exact solutions of the flow, because there are whole families that are equally good. So now we should use, again, the technique we used before. Whenever we see a marginal eigenvalue, we either section if it's time, or slice it if it's a group symmetry, continuous group transformation. But now we'll have to dice the marginal eigenvector by determining what the marginal eigenvector is. So for example, you know, there'll be 3 for these two particles, because there'll be relative motions. They can get closer, they can shear respect to each other, they can turn around, and that costs nothing. So there'll be three things which are like slices. I'll call them dicing. They're not like slices because slices are exact. When you reduce a flow from a full state space to a slice, that's an exact transformation. No approximations are being made. It's just basically a choice of coordinates where you have motion in a shape-changing space, and then there is a motion, one coordinate for each marginal direction where you're actually in a full state space. That's called gauge connection, or God knows what, or reconstruction equation. So, what's dicing? You need some criterion that fixes these moving solutions, so you can actually apply a Newton and find a representative of the whole family of them. Now, for slicing, we use criterion of closest passage, but that doesn't seem to be a good idea because here we want to put in as far as possible. For example, if our original problem is on a torus or an infinite plane with rotation, but let's say it's on the torus, then we would like to put in as far as possible from each other, because then the overall, the smallest, and they'll be the most likely, almost exact solution of the system. So now remember how we did slicing. We said we pick one point, and then on every group orbit we pick the closest point, and that was given by extremal condition. But we can also pick the furthest away point when we have a loop. So instead of going this way and checking where the curvature of our state is the meaning local minimum, that means that all curvature eigenvalues are, let's say, negative. Then there'll be state far apart, which will be the furthest most state. It'll also satisfy the same equation, so it'll also be in the same slice, same horizontal plane as before. But now it'll have all curvatures negative because it'll be furthest away state. So that's my proposal. Use the eigenvector for each marginal direction to define a plane orthogonal to it, transverse to it, a dicing plane, which will fix the relative motion of the two objects, and use your Newton method to find a solution like that. Now, because dicing is not exact, that solution will not be exact solution. It will be slightly wrong, because the eigenvalues of this eigenvector are not marginal. They are almost marginal. But once you have that solution, you can now run the full space and find the closest possible solution to it. And I'm very optimistic that you will find sets of 2 vortices, 3 vortices, 4 vortex core, any number of vortex core which are sufficiently far apart from each other that overlaps of approximation, the isolated solutions, is small. And for each particle, you'll have to have, let's say in a plane, you'll have to have 3 marginal solutions per particle, so you will have to dice and dice and dice for each particle. They'll all have their separate little marginal eigenvectors, and you will use those eigenvectors to choose the dicing plane and find solutions which are most equidistributed on the torus, if that's the situation you're in. And with them, describe behavior in the patches, which means patches a part of the state space where you move one of the solution using continuous parameters. And it's almost like a group orbit. There is small correction because the symmetry is not exact. And patch has to be finite because when the two structures or any pair of the structures come too close to each other, then the patch is not a good description anymore. They start interacting strongly. So that's my proposal how to dice. It shouldn't be any harder if you know how to slice.